Okay, welcome. This is the second video on the final exam review. In the first installment we did problems 1 through 5, and we're going to pick it up at 6 here today. Not sure how far we'll go, we'll just see how time allows. Okay, we are going to use the definition of derivative. That is a specific process. Yes, the derivative of f prime of x, if y is f of x, the derivative f prime of x, we know that that is 2x minus 3. However, doing that will get you no points for this problem. The definition of derivative is our limit as h approaches 0 of f of x plus h minus f of x all on h. And that should lead us to 2x minus 3. It's nice to know, but we have to show the process. So that becomes the limit as h approaches 0, f of x plus h. F is a factor that takes things, puts them here, squares them, puts them here, multiplies them by 3, and subtracts them. So f of x plus h is x plus h, square it, minus 3 times x plus h. Minus f of x, that's minus this, it's minus x squared minus 3x, but there's our most common algebra mistake. We are subtracting all of f of x and put all of that on h. So now we pass this on to, that's calculus, we pass this on to an Algebra 2 student. Tell them, hey, simplify this guy for me. FOIL, x squared plus 2xh plus h squared, distribute with the negative, minus 3x minus 3h, distribute with the negative, minus x squared plus 3x. Again, that would probably be the most likely place for error in this process. All on h. And now here's how you could catch that error. Anything that does not have any term in the numerator that does not have an h in it, I expect to cancel. Here's an x squared minus x squared, good. Here's a minus 3x plus 3x, good. I've got these three terms remaining. 1, 2, 3. Each of those has an h in it. If I divide out h, I get 2x. Plus, there's still an h here, minus 3, and now I can put 0 in for h, and I get 2x minus 3. So our slope formula is 2x minus 3. The good news is we knew it should be. The bad news is we have to go through that process on here. And now we're going to answer everything asked. Use the definition to find that. That's one of our answers. I'm going to box it. Then find the slope of the curve when x equals 2. So that would be f prime of 2. F's derivative at 2 is 2 times 2 minus 3, or 1. And we're supposed to write the equation of the tangent line at that point. The tangent line at 2. Well, I've got my slope is 1. But now I need to know what point it's going through, so I go back to plain old f of 2. F of 2 is 2 times, that is 2 squared minus 3 times 2. That is 4 minus 6, negative 2. So I have an ordered pair 2, negative 2 with a slope 1. Y minus the y coordinate equals slope times x minus the x coordinate, which could be an answer. I'm going to put this in slope-intercept form. Y equals x. That would be minus 2 more, minus 4. That's a solution. Find the slope. Here's the solution. Then write the equation tangent line. And we got them. All right. Suppose u and v are functions of x that are differentiable at x equals 0, and that u of 0 is 5, u prime 0 is negative 3, v of 0 is negative 1, v prime, or v's first derivative of 0 is 3. Find the values of the following derivatives at x equals 0. So I'm finding the derivative of function u divided by function v. That is low, d high, minus high, d low, over the square of the thing below. And now it's just straight substitution. V at 0, plain old v at 0 is negative 1. U prime at 0 is negative 3, minus plain old u at 0 is 5. V prime is 3, all on v negative 1 squared. So I get positive 3 minus 15 on positive 1, or I get negative 12. Okay. This problem, derivative, is going to be 2 times u's derivative minus 3 times v's derivative. Constant coefficients survive differentiation, so it's just plain old 2 times derivative of u minus plain old 3 times derivative of v, plus, I'm going to treat this as the product 2u times v. I want plain old 2u product rule times derivative of v plus 2 times u's derivative times plain old v. So that is 2 u's derivative negative 3 minus 3 v's derivative 3 plus 2 plain old u 5 v's derivative 3 plus 2 times u's derivative negative 3 times plain old v negative 1. And it's probably worth going back and double checking. It's an easy problem, but it's an easy problem to pick a bad value from up here. So I get negative 6 minus 9 plus 30 plus 6, I get negative 15 plus 36, I get 21. Okay, so there is number 7. Number 8, we've got a rock thrown vertically from the surface of the moon at a velocity of 36 meters per second, so we'll come back and we'll deal with meters and seconds, reaches a height of position t equals 36t minus 0.8 t squared meters in t seconds. Find the rock's velocity and acceleration as a function of time. So velocity based on time is the first derivative of position. That is 36 minus 1.6 t. Acceleration is the second derivative of position, or the first position of velocity. The derivative of 36 is 0. Derivative of negative 1.6 t is negative 1.6. Constant acceleration. Okay, how long did it take the rock to reach its highest point? Well, it reached its highest point at the vertex of this parabola. We could do this with Algebra 1 skills. We know this is an upside down parabola. We could do opposite b on 2a, and that's how long it took. We could also say if it was thrown up, thrown down, it reaches a velocity of 0 at its highest point. So I could say, when is velocity 0? Velocity is 0 when 36 minus 1.6t equals 0, or when 1.6t equals 36, or clear 36 divided by 1.6 is 22.5. So t is 22.5 seconds. How high did the rock go? Well, the rock, so what we're looking for is a maximum. We could be looking for when the velocity is 0 to find our maximum, but we've already found that. That's at 22.5 seconds. So how high did it go? It went S of 22.5 seconds, which is 36 times 22.5 minus 0.8 times 22.5 squared. So let's take that one. Actually, I'm going to shift calculators here and get something a little bit more sophisticated. And let's go 36 times 22.5 minus 0.8 times 22.5 squared. Then we get 405 feet. Okay, now, I think the next question may be a little bit ambiguous. How long did it take the rock to reach half its maximum height? Well, the rock went up 405, came back down 405. Half its height, half its maximum height is half of 405.2. half of its maximum height would be, or 405, excuse me, would be 202.5 feet, is what it's asking. Well, that's going to happen twice. I would probably say, I would probably reword this to say on the way up. How long did it take the rock to reach half of its maximum height as it ascended, or something like that? In other words, I want its position to be 202.5. So its position function again would be 202.5 is, let's come back down here, 36t minus 36t minus 0.8 t squared. So that gives me a little quadratic to work with here. I'm going to get, I like having positive t squareds when I'm doing quadratic formulas, so I'm going to add 0.8 t squared minus 36t. I'm going to leave 202.5 over here so it stays positive, equals 0. And I'm going to go to quadratic formula with that. Now again, if I graph the flight of the rock over time, here's what I know. I know it reaches, this might be useful for another problem later anyway, at 22.5 we have our max of 405. I'm trying to figure out when it hits half of that. So it hits it here, it hits it here, we're only looking to the one to the left. Opposite of b, 36 plus or minus square root of b squared, 36 squared, can use the negative would get absorbed, minus 4 times a 0.8 times c 202.5 all on 2a 1.6. Now the 36 plus would be the point to the right. I'm only going to use the minus version of this. Let's go clear, let's go alpha, let's do a fraction here, and I'm going to get 36. I'm going to use the minus version. Square root of 36 squared minus 4 times 0.8 times 202.5, and jump down to the denominator, double check, make sure I've got everything right there, divide by 1.6, and hopefully my answer makes some kind of sense. And I get 6.590. Now, that does make some kind of sense because it took 22.5 to get to the top, and you may say, well, why doesn't it take half that? Well, it's going fastest at the beginning, then slowing down, slowing down, slowing down, so it should get to the halfway point before 11 seconds. Okay, how long was the rock aloft? Well, the rock was aloft from time 0, because 0 is a 0, until it hit the next 0. So I just want to find when 36t minus 0.8t squared equals 0. If I factor out a t, I get 36 minus 0.8t equals 0. I get t equals 0, and t equals, let's see, I would subtract 36 and divide by negative 0.8. That's 36 on 0.8. So t equals 0. 36 divided by 0.8 is 45. So t equals 0 and 45. So at 0 it took off, at 45 it landed. That is 45 seconds. And 45 should be pretty comforting because as long as it took to go up, we would expect it to take that long coming down. So double 22.5, we got 45. All right, number 9. Does the graph of y plus 2 sine of x have any horizontal tangents in the interval 0 less than or equal to 2 pi? If so, where? If not, why not? All right, talk calculus to me. Horizontal tangents. Horizontal tangents. First derivative equals 0. It's just different language. Same thing, calculus language. First derivative equals 0. So our first derivative is 1 plus 2 cosine of x. If we set 1 plus 2 cosine of x equal to 0, we get cosine of x equals subtract 1, divide 2. When is cosine negative 1/2? Well, cosine is negative 1/2 when x on r is in ratio negative 1 to 2. That gets me to here. And there. And I'm allowed to rotate from 0 to 2 pi. That's 60, 60, 60, 60. That's two 60-degree angles, or 2/3 pi and 3/4 pi. Okay, we will continue. I got a little bit more time here, so we will continue on from there. Next page, a lot of just derivatives here. These are going to be little quick hitters on our quiz, and when we take the final, it's nice to have these on there. It's such a huge portion of what we're doing in the first semester. So hopefully we recognize this is a product rule. dy dx would be plain old first, x squared times derivative of second, secant squared x, plus derivative of first, 2x times plain old second, tangent x. But as always, we are going to take these and put them in their more useful form, which is factored. So I can factor an x out of each of these, and that's about it. And I get x secant squared x plus 2 tangent x. There's my dy dx. Simple. Well, this is simple too if we remember cosecant's rule for derivative, dy dx. Cosecant's derivative starts out as just the opposite of cosecant, so that becomes positive cosecant, counters that negative. Leave the baby function alone, times cotangent, leave the baby function alone, and then outside of those parentheses, multiply by, treat the baby, 2x plus 5. And here's the good news. That is already in factored form. So we are done. C, hopefully immediately we recognize this is implicit differentiation. Hopefully next we recognize this is a product rule. Derivative of 3xy, leave 3x alone, derivative of y, dy dx. Take the derivative of 3x, 3 times plain old y. Plus derivative of y squared with respect to x is 2y dy dx. Equals derivative of x, 1. Derivative of y with respect to x, dy dx. All of my dy dx is to one side. I'm taking them to the left. 3x dy dx. I'm leaving 2y dy dx. I'm subtracting over dy dx. On the right side, I'm leaving 1, but I'm subtracting over 3y. When I factor dy dx out, I'm left with a 3x plus a 2y minus a 1. So dy dx equals, when I divide to get dy dx alone, I get 1 minus 3y on 3x plus 2y minus 1, and there is nothing I can factor and reduce. Done. Okay, D, product rule again, with a quotient, not a quotient rule, but a chain rule. So dy dx may have some simplifying left here. Let's see what happens. First, times derivative of second, 4, leave the baby function alone to the third, treat the baby, derivative of 2x minus 5, 2, plus derivative of first, 3x squared, leave the second alone, 2x minus 5 to the fourth. And now we're going to factor that. Before I do that, I think I'm going to get this 8. 4 times 2, I'm going to write this as 8x cubed, 2x minus 5 cubed, plus, nothing to simplify here, 3x squared, 2x minus 5 to the fourth. What can I factor out of here? Nothing out of the 8 and 3. I can factor out a pair of x's, though. And I can factor out 3 of these 2x minus 5's, which would leave me with, from this first term, an 8 and one of the x's. From the second, I would still have a 3, and I would still have this 2x, one of these 2x minus 5's. And I think we can simplify this in one step. I've got an x squared, I've got a 2x minus 5 cubed, and in here I've got 8x and 6 more x's, 14 x's. I've got a 3 times a minus 5 minus 15. Okay, nice easy little quotient rule here. dy dx, low, d high, minus high, all of it, d low, over the square of the thing below. Of course I can't cancel these. This is part of a term. So, simplifying, let's just do this in one step here. I get 4x minus 4x cancels. I get minus 2 and ultimately minus 4 for negative 6 on 2x minus 1 squared is d, not dd, dy dx. Okay, we will continue here. Still finding derivatives. I might want to think of this as ln x to the 1/2, which of course is 1/2 ln x. dy dx then would be 1/2. Constants survive. Constant coefficients survive derivation. That's a constant coefficient, so 1/2 survives. Derivative of ln x is 1 on x, so I get 1 on 2x. Nothing to it. dy dx. Product rule. Plain old first. Derivative of the second stays e to the x, plus derivative of first, 2x, plain old second, e to the x. Factor out anything we can. I can take an x out. I can take an e to the x out. I'm left with one of my x's, and I'm just left with 2. Why do we insist on factoring? Because right now I know where the slopes are all horizontal. When x equals 0, when x equals negative 2. That's oftentimes when we find the first derivative, what are we going to do? We're going to set it equal to 0. We're going to look for non-differentiables. Okay, this one, right now this is extra credit. I think eventually we'll work to learn those, but for the time being, extra credit, so you can work through that. Be prepared for any of the 6 trig functions there. Y equals log base 2 of x minus 3. I wish it was ln. If it was ln, it would be this easy. dy dx equals 1 on x minus 3, and then it would be times the inside derivative, which is 1. But it's not ln, it's not log base e, it's log base 2, so I punish it by putting it in ln jail, ln2. I wish you were an ln e. Okay. And that is it. Okay, J. Y equals 3 to the. Now, if this was e to the, because e is just a number like 3, but e is a special number. E is our favorite calculus number. If it was e to the, this would be dy dx equals, it would be e to the, so 3 to the, it would just be x sine of x. And then I'd have to take the derivative of sine of x. So that's a product rule. So that would be times x times cosine x, plus derivative of x1 times sine of x. But it wasn't e, so I punished 3 for not being e, adjust for it with ln3. And that is it. Okay, I think I will have time for one more problem, and this is one of our big just the basics. I mean, this is really almost, other than like definition of derivative that we just talked about earlier in this video, this is almost a first semester test unto itself. Show a complete graph and identify the inflection points, local max, mins. I'm going to find derivatives. So my y prime, first derivative, is 3x squared minus 18x minus 21. So that can go right here, 3x squared minus 18x minus 21. If you want to factor that, great. I'm going to get my factoring done up above. If I set this guy equal to 0 and factor out a 3, I get 3x squared minus 6x minus 7, or 0 equals 3 times x minus 7 times x plus 1, and therefore we've got derivative equal to 0 at x equals negative 1 and 7. Now, I can put values between negative 1 and 7, 0. Put in 0 and I get positive times positive, it's negative. And I can put values in out here and do an 8. I can put in a negative 2, it would be positive. But if I know this is a third degree polynomial and it's positive, I know it looks like this, so it goes up, goes down, goes up, down, up. It has a max, it has a minimum. It has a maximum at negative 1, it has a minimum at 7. I know those things ahead of time. Second derivative, 6x minus 18. The second derivative is 0, at 3. At 18, divide 6. At 3, the second derivative is 0, and I put the 0 there. Now, I can put a value bigger than 3, like 4 in here, and I get 24 minus 18 positive, but I knew that this was going to be eventually concave up. I can put a value like 0 in here and get negative. But to the left of my inflection point, I knew I had to be concave down. So we know those things. I just need to find f of negative 1. So that is negative 1 cubed. I should rewrite the function down here. Here is y equals x cubed minus 9x squared minus 21, x minus 11. So f of negative 1 becomes negative 1 cubed is negative 1, minus 9, the negative gets absorbed, plus 21, minus 11 when I put negative 1 in. Let's see, so I get minus 21 plus 21, oh, how about that? I get 0. We have a maximum of negative 1, 0. We have a minimum, f of 7, and I'm going to use calculator on that guy. It might be, if I remember right, it might be negative 256, but let's see. I get 7 cubed minus 9 times 7 squared minus 21 times 7 minus 11. And I get negative 256. So negative 256 is my minimum. Point of inflection, I want f prime, my inflection, my concavity goes from negative to positive and hits 0 at 3, so I want f of 3. So here we go. So maybe I can do this. Second enter. Let's go back and change all of my 7s to 3s. Will that work? 3. And this answer should be half that, because I was between 0 and negative 256. The inflection point halfway between. Negative 128. That works on cubics. So my point of inflection is 3, negative 128. Function is increasing when the slope is positive. So this should just be a repeat of what's going on here. Negative infinity to negative 1 in union with 7 to infinity. It's decreasing when the slope is negative, negative 1 to 7. Concave up, positive second derivative, 3 to infinity. Concave down, negative second derivative, negative infinity to 3. Let's graph this guy. At negative 1, I've got a maximum of 0. At 7, I've got a minimum of negative 256. Halfway between there, at 3, I've got an inflection point halfway down. So this is cupping down, cupping up. I could probably emphasize that cupping a little bit more. And from this point on, it heads up. Okay, I think that is where I'm going to call it a day for this video. I will have probably one more to handle 12, 13, and 14, and check it out.